Having defined the ordering inside a candidate for the real number, we proceed to define the algebraic operations of addition and multiplication. So the algebraic operations in R. So given A and B that it can cut, we define A plus B. Remember, this plus is like a new plus. It is the set of numbers of the form A plus B, where A is in the set A and B is in the set B. Okay, so this is a definition of an operation. This is not our traditional plus. It is supposed to extend our notion, our usual notion, but it's not. I mean, this symbol here does not stand for the same operation. First of all, we're not dealing with numbers, but with subsets of rational numbers. Okay, so this operation here should map two Dedekind cuts into a Dedekind cut. In order to be well defined, if we define a set this way, I mean, this is well defined as a set, but we need that A plus B, which is a set. Here is also Dedekind cut. We want to add Dedekind cuts and obtain new Dedekind cuts. So in the book, actually gives an example. If give an example, a proof of the property C2. So let's recall that if we want the operation to operation plus to be well defined, then A plus B, which is a set, should be a Dedekind cut. So remember that we need to show three properties. The first one being that A plus B should not be the empty set and should not be all of Q. Of course, if A and B sets are not empty, you pick just one element in A, one element in B, and when you add those two elements, you obtain an element in A plus B, so A plus B is trivially not the empty set. You can also prove that you cannot produce all the rational numbers by adding one element in A and one element in B. Okay, so that's an exercise for you. So this corresponds to property C1. And C3 is also left for you as an exercise in 8.6.5, which is part of your homework. But let's see, so see why C2 holds for this definition of A plus B. Remember, what do we want to show is if we have an element in A plus B, then any rational number smaller than that element should also be in A plus B. Okay, so we start by letting Q or R be an element in A plus B. If R is an element in A plus B, it means that R is equal to A plus B for some A in A and some B in B. A and B are not necessarily unique. We're just saying that there's at least one A in A and one B in B such that R is equal to A plus B. I mean, all the elements of A plus B are elements or numbers that can be written as a sum of an element in A and an element in B. Sum of an element in A and another element in B. Okay, so by definition of this set A plus B, R must be obtained from adding one element in one set and the other set in the other that they can cut. But it doesn't mean that A and B are unique. You can obtain R as the sum of many numbers, many different numbers. But we know that there's at least one A and one B, such that this is true. Okay, otherwise R would not be in the set A plus B. Okay, so then let S be a rational number such that S is less than R, which is again then equal to A plus B. By the properties of rational numbers, this over here implies that S minus B is less than A. Right, we can subtract B on both sides and we get this inequality. Now, remember that A is an element in A, right, in capital A. And you know that any number that is smaller than some element in A must be in A. Remember, if we go back to the property C2, if R is an element in A and if Q is in Q smaller than R, then Q also belongs to A. So if we go down here, this is our Q, and what we've shown is that this Q is in A. Because it's a rational number, so we started from S being a rational number, and because we are considering subsets of the rational numbers, B is also rational numbers. When we subtract rational numbers, as in here, as in Q, we get a rational number. So we have a rational number that is smaller than element A in A. Then that rational number must be in A as well. But then we can write S as S minus B plus B, and this is in A, and this element here is in B, and the set A plus B is a set of all rational numbers, as is a rational number. All rational numbers that can be written as the sum of one element in A and one element in B, which is the case here. So this belongs to A plus B, which is what we wanted to show. Okay? So then what we leave for the next video, a few remarks about the existence of an identity element for addition and inverse, and finally we define the product. After this, we'll be done with the algebraic property, so we will have only accomplished the construction of a set that enjoys the same algebraic properties that Q has. But now, we also need to show that the operations we have are compatible with this new order, so we can subtract things and add things on both sides and get the cancellation properties, say. But that will be kind of easy, and that concludes the proofs that this is an ordered field. But then we need to add that property the Q lacks, namely the property that we had that every bounded set of these Dedekind cuts has the least upper bound. Okay, and this is what differentiates R from Q. And the very, very last step is to show that Q is actually embedded into this set, which we'll do in the very end. Okay, see you in the next video.